Okay, I guess we can somewhat start, since we said that we aim to start sharp. By the way, some people may mention if there's any office hours, so maybe we can set up some time in case you're interested in talking to me. And so that would be Monday at 5. And so that would be my office, which is VA 6206, or we can do it online, or can do on Zoom. I'll send you the link. Okay, very good. So okay, so we can get started with the second class. So in fact, first, before going into the random walks on groups with hyperbolic properties, that is, the biggest part of the course, we'll still want to discuss the basic results in random walks that we discussed yesterday. I mean, 2 days ago, we just announced this is probably the most famous result. So I feel like we should still discuss its proof. So there's a famous theorem of Polya that says the simple random walk on ZD is recurrent if and only if D equals 1 or 2. So once again, in low dimension, your walk will be recurrent. So we'll come back to the origin infinitely often with probability 1. While if D is higher, somehow you have more space to wander around, and it turns out that this is enough for your walk to sort of diverge. Okay, so yeah, let's discuss this proof. So this is sort of the more probabilistic proof that we're probably going to see in this course, because it's so first of all, let's recall. Let's see a criterion that we can use to determine whether a random walk is recurrent. So and the criterion is the following. So we let Pn of xy to be just the probability that the walk goes from x to y in n steps. So this would be, according to our notation, the Wn equals y, given that W0 equals x. And if this is the case, then we define M to be the series Pn from 0 to 0. So here we have a random walk on ZD, for instance. So we pick base point. And so this is the series, which could, it could converge or could diverge. It's a series of positive non-zero, non-negative numbers. And so the lemma is then the random walk is recurrent. Well, if and only if this series is divergent. So first of all, intuitively, this makes sense, at least that this is the right direction, because you see, this being large means that you have a high probability of coming back. And so if you sum all these probabilities, you get infinity. And if this is infinite, means these are large, it means that you have a high probability of coming back. So this is the intuition, and well, this we can prove this lemma. It's not so hard. So you can notice the other fact that, so first of all, M is intuitively is the average number of visits to 0. So why does it make sense to think that this is the average number of visits to 0? Well, because if you read this again, right? So what is Pn 0, 0? Is the probability that time n is one such visit. So for each k, pk00 is the probability that time equals k is a visit. And so you're taking the sum of all those, and this would be the expectation of the number of visits. So this is the intuition. And what else do we need to show? Well, we can let u to be the probability that the walk returns to 0 at all. So at least once. So you start you have your walk on the grid. And you just take whatever the path is, but either it returns to 0 or not. So let's call the probability that the walk returns to 0 u. And then it's an exercise to write m as a function of u. So let's see why. So it's like this. So we note that the probability that the number of visits is at least k. So what does it mean that the number of visits to 0 is at least k? It means that the walk, first of all, comes back once. Now, if it comes back once, okay, probably the visits is at least 1. Now, if you need at least 2 visits, you want the walk to come back once and then come back again. And since this is a random walk, there is an independence of this return time. So there's a Markov property. And so basically the probability that the number of visits is at least k is u to the k. Because basically once you return once, you can kind of forget everything that happened in the past, and you have to do it again. So you get u again, so it's multiplicative. So okay, and so now once we have this, then it's really clear how do we get m? How do we write m as a function of u? Any takers, maybe? So m is the expectation of the number of visits, right? Expectation of the number of visits. So it's an integral. And now my favorite way to write an integral, and many people's favorite way, is the sum of the probabilities that this variable is at least k. So for each k. And so now we just take this up. So this is just sum over u to the k. Yes, and then we can kind of see what happens. So the question is m infinite or not? And so, of course, there are two different. So this is a geometric series. So of course, we would like to write this if u is less than 1. And if u is equal to 1, well, this diverges to infinity. So what we can say, we say that m equals infinity is if and only if u equals 1. And what does it mean to u to be equal 1? Well, it means that with probability 1, the walk returns to 0 at least once. So this already gives you sort of half the theorem, because you see, if the random walk returns infinitely often, then it returns at least once. So m has to be infinite. But then again, this is a random walk. So if it returns with probability 1 at least once, then you can repeat the same process. And the second time also, the second return also happens with probability 1. And so you have an intersection of sets of probability 1, so it has probability 1. So this is equivalent to say that with probability equals 1, the walk returns infinitely often. Okay, so this is sort of a little kind of famous lemma in probability. Okay, so maybe are there any questions about this lemma, this proof? So, is it too fast? It's good. Yeah, so probably, yeah. So okay, so and now what? And now we just have to check in different cases when you have the z to the d, we have to check whether this series is divergent or convergent. Okay. So now let's check. So let's do for d equals 1, where we want to show that the sum of Pn 0, 0, well, this want to show this is divergent, because this would be equivalent to the random walk being recurrent. And now, fortunately, in one dimension, we can do the calculation. We can do a little bit of combinatorics. In one dimension, it's fairly easy, combinatorics. So if this is 0, so again, it's simple random walk. So we go right or left with probability 1/2. So what's the probability that you're coming back to 0 after n steps? Can we write combinatorial formula for that? Does anybody? Some of you have probably seen it before. So what? Yeah, that's a good point. So it's 0 if n is odd, because every time you have to go either right or left, and the number of rights has to be equal to the number of lefts. Right. So if n is even, what do we have to do? Well, again, we have to choose the right and left, right, left, left, right, something like this. And we want to say that the number of rights is the same as the number of lefts, which has to be n/2, because we have n steps in total. And so, as you said, like you're going to get t, you're going to get n, choose n/2. And then, well, so this is the number of possible configurations, because you have to choose n/2 out of this n. And then the denominator is 2 to the minus n. And now we just need to play a little bit with this and estimate this binomial coefficient, which you know is n factorial divided by n/2 factorial squared, 2 to the minus n. And how do we estimate binomial coefficient? Factorial. Yeah, so there's a good old Stirling's formula. Of course, there are various more and more refined ways, but n factorial is basically what? It's n/e to the n, I think. Then there's another small factor, which is square root of n, I think. Let me check. Yeah. Yeah, and there's also 2 pi. If you really want, you can say it's like that. But okay, in fact, to determine the rate of growth, it doesn't matter the 2 pi, so let's forget about that. And it's kind of nice, this exercise, because if you've never seen it, like it's like you n/e to the n times square root of n, and in the denominator you get n/2, so n/2e over n to the n/2 to the square root of n squared, and then you still have this 2 to the minus n. Right? And then let's see what happens. Yeah, so squared, is n, yeah, so there's this square here. Yeah, exactly. So if you work this out, did I make a mistake? Yeah, but it's the same rate as square root of n. So I'm forgetting the constants. Yeah. But yeah, you're right, of course. Yeah. Okay, so let's see. So what happens? So you have n to the n, square root of n, e to the n. This is this thing. And then here, what do we have? Well, there is this square here, right? So in the denominator, you have, again, n to the n. Then you have 2e to the n. So you have 2 to the n, e to the n, square root of n squared, so it's n. And then you have 2 to the n. So there is a lot of simplification. Like that. And so it's like 1 over square root of n. Yeah, when I put double squiggle means I forget in the multiplicative constant. If I put only one squiggle, I have to be more precise, so I don't need it. No. Okay, so far so good, because of course this implies the square root that this guy is of the same rate as this one, which is infinite. So somehow the returns to 0 in the line are polynomial, are some power of n, but this power, you see, is somehow small enough so that if you do 1 over it, it's big enough that it diverges. Okay, so that's a sort of standard exercise. Now, what about if we go to higher? What about if we go to higher dimensions? So for d equals 2, huh? Now we have square grid. In many ways, even more classical. Okay, and we have 4 options to move. So we have, let's call it traditionally north-south, east and west. The hardest part is to remember which side, where is east and where is west. I think is that right? Yes. North and south, everybody knows, but east and west is a mess. Well, okay, so now, again, it's the same thing. So if n is odd, clearly there is no return to 0, because you have to, take the same number of norths as south and the same number of east and west. So we have to check what is p2 to the n, 0, 0. p2n, okay? Now, I'm sure there are many ways of doing this. So the thing is, yeah, so what's my favorite way of doing this? There is a bit of a trick here for 2 dimensions. And the trick for 2 dimensions is that you can reduce to the 1-dimensional case in the following way. So we have 4 targets. So we need to go in these 4 places with the same. So we have, the famous coin that has 4 sides. But can we toss 2 coins instead? And the answer is yes. How can you toss 2 coins to represent these 4 choices? So here's the trick. So you look at this walk. You instead of going north, south, east, and west, you can go first. You toss a coin and you decide if you go northeast or southwest. And then you toss a second coin and you decide if you go northwest or southeast. And of course, if you started with here, if the first move was here, then the second one is like this. We don't have a Pokemon to show this, but we can imagine Slowpoke that goes around. Yes. So you see, this is a kind of interesting trick in the sense that you can decompose with this walk in 2 dimensions in 2 orthogonal 1-dimensional walks, because again, every time to go back to 0, you still need the same, you still need that the number of green arrows that goes in the northeast direction is the same as the number of green arrows that goes in the southwest direction, and in the northwest and southeast. So how do we determine this this probability then? Yeah, it's the same thing. It's just the square of the previous one, basically. Yeah. So because again, this is the probability that the number of northwest choices equals the number of southeast choices, and the number of northeast choices equals the number of southwest choices. But these two things are completely independent of each other. So we are actually in a pretty good situation. So this is just a probability that you know, for instance, the number of northeast equals the number of southwest squared. So this is the trick, that you can split it into two independent ones. And so this is like 1 over square root of n, which was the one for one dimension square. And so clearly this is 1 over n. And so again, the sum of Pn 0, 0 diverges because each of them grows like 1 over n. So far so good. Now we can kind of guess maybe what happens next. Because in one dimension, the probability grows like 1 over square root of n. In 2 dimensions, grows like 1 over n. And what about in 3 dimensions? What do you think? Yeah, that's exactly right. So in fact, so the fact is that we're not going to prove it in the whole generality, but we will prove something in dimension 3. But in general, it's true that on ZD, the probability of 2n coming back to 0 after n steps, this is of the order of 1 over n to d over 2. Clearly, this would be enough because the fact, of course, would imply the theorem, because, of course, if you take the sum of P2n, and of course, if n is odd, it's still 0. So this would be sum of 1 over n d over 2. And so, of course, this would be exactly infinite if d equals 1 or 2, and finite if d is at least 3. However, so this is all true. There is, however, a sort of problem in a sense that the computation becomes way trickier if you're in higher dimension. So in 1 dimension, we could just do the binomial. In 2 dimension, we reduced the 2-dimensional case to a product of 1-dimensional cases. Now the question is, how do we reason for what about d equals 3? So here you would have a 3-dimensional grid. So okay, now already it's complicated to draw. Start with a grid like this. You have a cubical grid sorts, right? Something like that. Really quite tricky to draw. Can we move green? something like this. And so you have how many directions do you have here? Yeah, we have 6 directions. You have north and south again. You have again east and west. And then you have one more direction, which is let's call it inward, inside the board, and outward towards the outside of the board. Okay. Now here's a question: can we interpret this random walk in a 3-dimensional grid as the product of independent 1-dimensional walks? Let's think about it. So how many options do we have here, right? Yeah, here you have 6 options. And what if I do three independent 1-dimensional walks? Yeah, that's more or less the fact, right? So because you see, if you think about it, so suppose you do a walk in the 3 directions. Suppose I do three walks. So one is up or down, one is left or right, and the other one is in or out. So maybe you get something like this. So, if you consider all the possible options, you would have 8 options. And in fact, what you can see geometrically, this will bring you to the 8 vertices of the cube. So if you do it, you can do up or down and left or right, and then in and out. These options will get you to the 8 vertices of the cube, which is not what we're trying to do here. Here we want to go to the faces. So we have, we choose what it's like choosing one face. So why is it easier in 1 dimension, in 2 dimension rather instead of 3 dimension? Well, if you think about it, what we did here is like we have a square. And so we have the faces of the square, so the sides, which are the original one. And we consider the dual, so that if we do the walk here, we do the walk in the dual tessellation. So now the dual to square is still square. Okay, not the one I drew. Right? So if you think about it, if you do like that, you still have square. So, but if you look at the cubical lattice, what's the dual to the cubical lattice? It's an octahedral lattice. So if you do so it's not this. There is no self-duality in higher dimension, and this is more or less the reason why it's not completely trivial to compute this. But we can still at least estimate it. So this will be the sort of last combinatorial problem in this whole course, I think. So how do we estimate it, right? So again, we need to compute P2 and 0, 0. So what do we have? We have these 3 types of ladders, right? So we have we have 2n such positions, and we have to fill them with what? With S and W, or I and O, or S and N, and E and W. And what's the constraint that we want? We want that the number of S equals the number of N, the number of I equals the number of O, and the number of E equals the number of W. Of course, in total is 2n. So another thing that comes from here is that the number of S plus number of I plus number of E has to be n. Right? Aha. So can we write this as a binomial or trinomial coefficient here? Any brave person who wants to write this? What do we need to do to count this? Yeah, it's a sum, right? It's not going to be just one thing, but basically, what do we have to do? So, okay, well, first of all, you have the 6 to the minus 2. No, this is just the denominator, right? So let's call k the number of, s's that you put, for instance, and then j, and then of course, so the next one will be just n minus k minus j, right? Okay. So yeah, so we have to choose k and j. So it's like k. You have to sum over k and j's between say 0 and n, and maybe that k plus j is less than n. Right? And now suppose we know k and j, then it's a bit easier because we have to choose right? So we have to choose the positions where we put the s, and then we have to choose the other positions and so forth, right? So if you do this, so the solution turns out to be like this. So you have 2n, choose n, and then you have n factorial divided by a factorial j factorial, n minus k minus j factorial squared. So let's see what kind of choosing are we doing here. So first of all, we have to choose n over 2n, right? So first of all, we choose, so we divided this into the sort of the left labels as I or E, and the right type of labels, right? So we have to choose n out of the 2n that will be labeled either as I or E. Okay, and now once you have that, out of those, we have to choose, right? We have to choose k of them out of the n that will be labeled S. So this would be n choose k if you really want it write it like this. And then how many are we left with? Where we have n minus k left, and we have to choose j of them. Now, if you do this computation, you realize that this is literally this thing here, because it's n factorial, k factorial, then you have n minus k factorial here that simplifies with n minus k factorial, and you're left with j factorial and n minus k minus j. Okay, and then you have to do the same. So first of all, you pick this. Let's pick this white labels. So let's say we have 4, like something like this. This would be the white ones. And then once you pick the white ones, you have the other ones are from the other row. And so there's n of them, and then of those, and this is this choice. And then once you have that, you write this. And it's twice because you have to do it one for the left column and one for the right column. Okay, so we wrote a formula. And now what we would like to say, and that this is roughly 1 over n to the 3 halves. Okay. A bit tricky, but at least if I want a bound one way, it's not that enormously hard. So suppose that we want to show that the run or walk is transient, so it means that this series is convergent. So you just need an upper bound, and the upper bound is easier. Why is the upper bound easier? Well, if you look at this coefficient here, this is like a trinomial coefficient, right? So it's like you have a plus b plus c to the n, and you're looking at a coefficient for k, for a to the k, b to the j, c to the n, k minus j. And so trinomial coefficients are like binomial coefficients. If you look at all of them with fixed n, which is the biggest one? The middle one is the biggest. So we can say that whatever this number here is, if we take k, j, and n minus k minus j to be the same, so they're all equal n over 3, this is the biggest one. So we get the following. This is s6 to the minus n to n over n. And then we still have the sum over k and j plus j minus n. And then we have the following. We replace this by n over 3 cube square. Okay. And then we have to estimate. So this one does not depend on k and j, so we can put the k and j here. K plus j is less than n, and these are positive. It's like 1. So what is that sum? No. So it's a trinomial coefficient. So if you do 1 plus 1 plus 1 to the n, because you're summing over all possible options. So it's like that. Okay, and so we're in good shape now, because we reduced ourselves to this, well, not so great looking, but in fact it's not super complicated. 3 factorial 6 to the 3. Yeah. And now again, you have to write down the Stirling formula once again. I think maybe maybe we don't we don't need to do it, but yeah. So basically, in the end, you just write the Stirling formula once again, and indeed this gives you 1 over n to the 3 halves. You see that there's a power of 3 in the denominator, which I think with the square root of n in the Stirling formula would give rise to this. Okay, so yeah, this is a bit of a computation which you may or may not enjoy, depending on what you like in math, but at least level it's still doable. Now, as the dimension goes up, things get more complicated, but okay, more or less, I think this type of bound would still work. The lower bound, well, is trickier. Yes. Okay, so that shows that the random walk, the simple random walk on Z cube, is transient at least. And so remember, remark that we discussed last time is that on ZD, let's say on Z cube, the random walk, the simple random walk is transient. But the drift of the walk, so the speed, is still 0. So it is going to infinity in a way, but it's doing so very slowly. And so it's very different from let's say from the simple random walk on a 4-valent tree, for instance, where L is positive, as we discussed last time. Because when L is positive, then the walk also is transient. That's a stronger. Okay, are there any questions? Okay, so now we start with a chapter in actual ergodic theory, which will give some basic facts about ergodic theory that we will use a lot in our next work. And in fact, at this point, the difference between ergodic theory and probability in many ways is that in ergodic theory, you really cannot estimate things precisely by doing some computation like this, by estimating doing the analysis and computing the coefficients, but it's more about things that happen almost surely, or on a set of full measures. So these are sets that maybe we cannot really control very well explicitly, like effectively, but we give this sort of statements. Yes.
On Z2.
Yeah.
So in Z2, like you gave this, so you can think about like the graph you drew is just the Katie graph with the standard inheritance set.
Yeah.
If you pick a different finite inheritance set for Z2,
yeah.
Do we know anything about if it's still recurrent or not?
Yeah, of course, there is another option. So it depends whether the barycenter of the walk, you see. So of course, you could say, okay, I go up with probability, 2/3, and I go down with probability 1/3. And I can even make it so that, okay, 2/6, maybe 1/6, and then you still go 1/2 and 1/4 and 1/4.
Maybe like I have more direction. They add the elements, for example.
Yeah, but what does it mean to do uniformly, right? So the issue depends on what is the barycenter of the measure. So if the weights in all directions cancel each other, then it's still recurring, and the drift is 0. Otherwise, the drift will be pointing, the net drift will point in some direction, and then it will be non-zero, and then of course it will be transient. So in Z2 is somewhat easy to control, because somehow, again, you can still in abelian groups, you still have this sort of, you can sort of decompose the walk still in different components. Yeah. Okay, good. Other questions? Yeah. Okay, so what is the main object of study in ergodic theory? Well, so the idea of ergodic theory is studying systems that evolve over time, and from a probabilistic or measure theoretic point of view. So typically, the main object is a measure preserving system. And so what is a measure preserving system? Well, we start with the space, so that maybe we call X, and it has a measure, let's say nu or p, depending. Maybe we can call it p, since it's mostly going to be probability for us. So, and of course, secretly there is a sigma algebra that so this would be a measure space. And in fact, most of the time we will assume that p of x equals 1. So this will be also called the probability space. But for several theorems in ergodic theory, this is not needed. But I think in this class will always be the case. And of course, so A would be sigma algebra, and P would be a measure on this sigma algebra. And well, often we will not mention the sigma algebra, so it will mostly be the Borel sigma algebra when you start with, say, a metric space. Okay, and then we have a map P from X to X. measurable map. So what does measurable means? Means that for every A in the sigma algebra, the inverse of A is also in the sigma algebra. Right? So remember, very, very important fact in ergodic theory, like you pull back sets. You very rarely say something about the image of a set, but most often you look at the pre-images. And we'll see in a second why. And so measure, but it has to be measure preserving. What does measure preserving means? Means that, so we say that T preserves probability P if probability of the inverse of A equals the probability of A for every A. And of course, there's also another way to denote this, which is so you see, we pull back sets, but we push forward measures. So the notation usually is that the push forward measure T star P, this is the push forward measure. Well, it's nothing else that T star P of A is probability of T inverse A. So sometimes I will write the parentheses and then I will forget about it. So forgive me. Sometimes I already know that. So some people just don't put them at all. So. And then what's the third object that people look at in ergodic theory? Well, so you look at functions, and so you're probing your system. So you see, an intuition would be something like X is, X is the universe, for instance, and T is the map that goes from the state of the universe today to the state of the universe tomorrow. And we can ask questions about what is the probability that something happens today versus what's the probability that something happens tomorrow. So measure preserving system means that for every possible event that you have, like, the probability that today drinks is the same as the probability that tomorrow rains. Of course, the system has to be sort of pretty big for that for that to be true. Like, but so of course depends on how big is the system. Maybe over the whole planet Earth, maybe it's kind of correct. I don't know. But anyways, this is the meaning of such thing. And then the last thing is observables. So how do we probe our system? Well, an observable is just a function. It's just the function is a measurable function f from x to r. So again, measurable means that the preimage of every Borel set in R is in the sigma algebra. And so again, what is what this means? For instance, the usual example would be like the temperature. So F measures the temperatures today. And then so we can study the composition of F and T. So for instance, if you look at F composed with T, this means like you take the universe, you look at tomorrow, and then you measure the temperature. So F composed with T would be the temperature of them. So corollary of the definition is that if, and here usually we can write the whole thing, X, A, P, T is MPS, which is measure preserving system. Then Well, the integral of f composed with t in dp equals the integral of f dp over the set for any f, for any f measurable. Well, and integrable, so of course, so for instance, we could say f is in L1. That would be one way to ensure that the integrals are defined everywhere. As long as this makes sense, if f is positive and this integral is infinite, then this also is going to be infinite. So that's also true.
Is this a
Yes. No, definition, I've given the definition of measure preserving means that the push forward of the measure under t is the same as p, right? So and this is a corollary. The corollary is that the integral of every observable, when you compose with t, is the same as the integral of f. So again, if your system is measure preserving, so it's stationary under time evolution, the average temperature on the globe today equals the average temperature on the globe tomorrow. So this is the average and of this function f that you're using to probe. Of course, a very important example, which is where this sort of duality between functions and sets comes in, is that you can pick f to be the characteristic function of a set B. So B is measurable. So instead of saying the temperature, I could say, B is the set of days where it's sunny. So this function is 0 if it's not sunny and 1 if it's. So why is this example important? Because it ties the discussion between measures and sets, because f composed with t. So if you start with characteristic function of set B and you compose with t, this is nothing else than the characteristic function of the pre-image of B. I mean, this is more or less. This is extremely easy to see, right? Because y1b composed with t x equals 1 if and only if, well, t of x belongs to B, which is of course if and only if x belongs to the inverse B. So we probe. So in particular, so measure if you start with measure preserving system satisfies that the integral over x of 1b goes with t dp equals the integral over x of 1b dp, right? And in fact, if you write this down, what this is the, this is the integral of characteristic function of the inverse of B. So this is just the probability of the inverse of B. And on that side, this is just probability of B. So we go back to the definition of measure preserving. So we can, so using functions instead of just sets is a bit of an, extension. But remember the fundamental before we can finish. But let me just say the fundamental principle is the following: that for set, the way for a set A, the way you act by the dynamics is T inverse of A. For a function, the way you act is F composed with T. So you act like that. And for a measure, P, the way you act is push forward the measure. So this is the natural way to look at things, even though, yeah, they all interplay with each other very nicely. Okay, very good. So I think it's time to stop. But yeah, next week we will see more about ergodic theory and prove maybe one or two of the famous ergodic theorems. Any questions? Yeah.
T is like preserving.
Yeah.
Means like so the push forward measure is
Yeah.
just a
Yeah. 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 In fact, we will see some examples because it's a slightly counter. This fact that we're taking the per images is maybe slightly counterintuitive. For instance, the doubling map on the circle, the map X goes to 2X mod 1 is measure preserving with respect to the Lebesgue function. Because it has two preimages. So every set. So this map expands the measure by 2. But if you take a set, there are two preimages. And both preimages have size a half of the original one, and you sum all together.
Proof of recurrence for people want to do. How do you put the lemma for those cases?
Which lemma?
The lemma that says that equivalent look at the sum of p and 0, 0 being.
Mm-hmm.
I mean, any bigger than 2, these broad telling you're done. But for d less than 2, what do we do? For d equal 1 and 2, how do you put the lemma?
No. Wait. So the lemma is independent of the space you're looking at.
Yeah.
The question is how do you check that the sum is. How do you check that the sum is finite or infinite?
This infinite. How do we define this infinite?
Right. So torus are recurrences. So now we said this. So it's this. So m equals infinity is equivalent to u equals 1. So we prove this. Yeah, u is a probability of returning to 0. So right, yeah. So that's this. Yeah. So this was the. Yeah, this is the proof of the lemma, but we did prove it. Like, yeah, because m is the sum of u to the k. This is true in either case. Yeah, so we did this proof. So just look again on the proof. I think we did all the details there, but if there's something missing, let me know. But I think we did. Yeah. What?
Just replacing u was first mu. Mu.
No, it was always u. Maybe it was not written well. But it's all meant to be. Yeah.
Hi, Professor.
Okay,
Hi, Professor.
so see you next week.
Hi, Professor.
Hey, yeah.
Yeah,
you hear
I'm
me?
just yeah, can you hear me?
Yeah.
Yeah, I just have a question. So for the Poiseuille theorem, if you want to prove it for walks with finite variance, what are the other methods that you would use?
Yeah, let me try. Yeah, yeah, the audio is not. I think the volume is just too high. So can you speak again? Let me try to lower a little.
Yeah, can you hear me now?
I think it's a bit better. Yeah.
Okay. Yeah, I'm just wondering if you want to prove Poiseuille theorem for the walks with, say, finite variance, what are the other methods that you would use?
If you want to prove Poiseuille theorem for finite
For
variance.
walks, yeah, like
Yeah.
more general walks.
Yeah. Honestly, I'm not. I'm not sure. I haven't looked at this proof in in detail, but I'll look it up. I'll let you know. Yeah, honestly, I don't know at this point.
Oh, okay. Yeah. Thanks.
Yeah, no worries.